while I'm taking care of the screen, I have a question to you. Who is taking notes today? Okay, and do you know also who is taking notes on Thursday? In any case, a question came up about how it should be done, because on Thursday there's my class and then Linda's class. Linda prepared some notes usually, but maybe they're brief. So the question was, maybe it's a good idea that the person who takes notes on Thursday will do also notes. And then it will be 2 hours on Tuesday, 2 lecture hours on Tuesday, and on Thursday it will be 1 lecture hour and 1 TA. Does this sound reasonable to you? Okay, so let's go with that plan. Okay. So we're discussing the support kernel method with support vector machines. And I think that this will occupy us today most of the time. And so I would like to remind you that the idea was that that the problems which are linearly separable in n-dimensional space are limited by the dimensionality of the space, the number of dichotomies, at least for points on general positions, that can be implemented by a linear perceptron is limited by dimensionality, and therefore in order to implement a simple architecture that implements a dichotomy in more complicated cases, it sounds like one of the ideas is that maybe we can just take our points and embed them in a higher dimensional space, and then the problem which was not linearly separable in the original space will be linearly separable in the higher dimensional space. And what we're doing now is taking this idea and implementing it within the context of support vector machines. And so the architecture that we're thinking of conceptually, we will see later that what we actually do is different. But conceptually, we have our inputs x1 to xn, and we're generating from them a higher dimensional vector, an m-dimensional vector, phi1 of x, phi2 of x, up to phi m of x. And so just graphically, I will represent this by the fact that in principle, each one of these phi's can be a function of all the x's, so I will draw lines like this for all of them. And now m is typically larger than n. And now in this, and this is nonlinear. And now, so each vector, n-dimensional vector, is embedded into m-dimensional space, and now we perform a linear discrimination on this space. So now we take all these numbers, and we we generate a y phi, which is the sine of W transpose times phi. W transpose is m-dimensional. Now the nonlinearity of these functions, phi1 to phi m, is essential. Why is it essential? Because if these functions are linear, then we can draw it like this, but in the end what we're implementing is still a linear. We could just as well write this as some other okay, we can have some linear functions from the x's to this space, some m-dimensional weights here, but we could write the whole thing differently as a linear combination of the x's, and then we didn't do anything. We're still implementing a linear discrimination in the n-dimensional space. So in order for this in order for us to gain anything from this trick, these functions must be nonlinear. Okay, and I gave, I think, a second. And I gave, I think, some simple example for what these phis could be, but this is just an example. At the end of the lesson, on Thursday? Sorry, Sunday. No, Thursday. Okay, so now what we want to do is to perform the support vector machine learning algorithm, or implement a support vector machine on this space. And as you will see, what happens is that despite the fact that we're doing this embedding into a higher dimensional space, we end up doing something very similar to what we would do without this embedding. And this is why this technique became extremely popular. And so let's think about the dual problem for the SVM. So remember that when we solve the dual problem, we end up with weights. So imagine that we solve the dual problem for these for a set of examples, okay, with a particular embedding. Then we're going to end up with a W, which is m-dimensional, which we can write as a sum over the examples. So we'll have alpha mu, y mu, and now the m-dimensional vector corresponding to each example, right? So this is phi of x mu. And now what I want to do first is to observe that in order to know, to define our separating plane in the m-dimensional space, we need the alphas, right? We find the alphas. We'll discuss in a moment what we need to do to find the alphas. But suppose that we already have the alphas, what do we need to do in order to now make a decision for a new example? If we want to use to categorize some new examples, so we need to calculate the output of the network, which is the sine of W transpose phi of x. So for any new example, if we want to generate the output of our network, that's what we need to do. And this we can write as the sine of a sum over mu, alpha mu, y mu, phi of x mu transpose times phi of x mu. Okay. And now I'm going to define. I'm looking at this object. Sorry, this is not x mu. This is x, right? Okay. So now I'm going to look at this object and call it k of x mu x. Okay, maybe I'll write the definition separately. So k of x1, x2 is simply defined as phi of x1 1 transpose times phi of x2. And this is called the kernel. Why am I doing this? So this is a function, so this in general is a function of two n-dimensional vectors, right? These are n-dimensional vectors. To calculate it explicitly, we embed each one of them in the n-dimensional space and take the dot product in the n-dimensional space. Okay? But the strength of the kernel method, as you will see in a moment, is that often we don't really need to explicitly go into the n-dimensional space. There are many useful cases where we can calculate this directly in the n-dimensional space. Implicitly, we're evaluating this dot product in the higher dimensional space with its nonlinear embedding, but we can do something very simple in the n-dimensional space, so it doesn't cost us much that we have expanded, we have moved to a much higher dimensional space. You will see this later. But for now, let's say that we know how to, all we need to do to remember that we should know how to calculate this thing. It's always true that one possible way to calculate this kernel is to explicitly go to the space and do the dot product, but maybe we don't have to do it. And so the only thing that changed, therefore, is that y, relative to the case without the embedding, is that y is now the sign of sum over mu, alpha mu, k of x mu x, instead of simply the dot product in n-dimensional space, the regular dot product in x mu in n-dimensional space. And now what we need to do is what I want to discuss is what do we do to find the alphas for a given set of examples. Right, so remember that the strength.
What about the y mu?
And y mu, yes, absolutely. Thank you. And so remember the strength of the dual problem. The reason the dual problem is nice is that we need to solve a p-dimensional problem. The number of variables that we need to find has a dimensionality of the number of examples. And not the number of, not the dimensionality of the space. And this remains true when we embed it into a higher dimensional space. So, and let's discuss for a moment what we need to do in order to find the alpha. So this is just what we discussed before when we solved the dual problem. The Q, we need to find the alpha, we write alpha as the argmax of some function q under the constraint that all the alphas are larger than 0, where q of alpha is, if you don't remember, you should look at your notes. So it's a sum over alpha mu. Mu goes from 1 to p. Minus half of sum over mu and mu going from 1 to p. Alpha mu, y mu. And what comes next is the dot product in the n-dimensional space, and we've already decided to call that k. So what will come in here is k of x mu. Okay? And we discussed the algorithm, the Adatron algorithm. We discussed it with Neta, the algorithm that is used to actually solve this problem. And note that the only thing that's changed compared to the case without the embedding is that whenever we need to calculate here the dot product, instead of just doing the dot product in the n-dimensional space, we plug in this function of x mu and x mu. And so again, if there is an efficient way to calculate this thing directly in the n-dimensional space, we don't lose, it doesn't take us much more effort than doing a regular Adatron algorithm directly in n-dimensional space. And so just to be a bit more explicit, in the Adatron algorithm, there is this margin, which is called delta nu, and it was defined as the sum over mu, alpha mu, y nu, x nu, dot x nu, and this turns now in our case to sum over mu, alpha mu, y nu, k. Okay.
What was it in the other one?
This is something that you need to calculate in each step. The Adatron algorithm. I don't want to go into the details because it's a technical point, but it's just what I want to more explicitly note that the quantities that you need to evaluate when you're implementing the Adatron algorithm, the only thing that changes is whenever you needed to do, without the kernel method, you would do a scalar product of two vectors in n-dimensional space. You now replace it with the scalar product in the m-dimensional space, which again, if you wish, you can calculate it by embedding the two vectors in n-dimensional space directly and doing the dot product, but often you will be able to calculate this thing more easily, so it will not take as much effort as you might imagine. Okay, so now, yes.
What is so far the advantage of going to the m-dimensional space?
So again, the advantage of going to the n-dimensional space is that many problems that are not linearly separable in the original n-dimensional space will be linearly separable in the higher dimensional space. Okay? We know that the fraction of dichotomies that can be implemented by linear classification is higher the larger the dimensionality is, right? And in fact, it's when for high dimensionality there is a kind of a cutoff that if your number of examples is larger than the number of dichotomies, then the space, then most dichotomies will not be able, almost every dichotomy will not be linearly separable. So that's the goal of, but another way to put it is that there's a richer class of problems that are linearly separable in the high dimensional space and in the n-dimensional space. Okay? So let's now discuss some examples, and then you will see why I'm saying that sometimes you can calculate this k directly. So let's imagine that my phi of x is the following. It will look a little bit weird at first, but we'll see that it's not so weird. So it's going to be, so x is x1 up to xn, right? X is n-dimensional. And so the elements of phi will be first the elements of x, but I'm going to put in a square root of 2 in front of each one of them for my convenience. Okay, and then I'm going to add to this all the squares of the elements of x. So these elements of phi are depend linearly on the elements of x. But now we'll have something nonlinear, which is x1 squared, x2 squared, up to xn squared. And now I'm going to add also all the products of some x and some other x. But again, I'm going to put in here a square root of 2 in front of it. You will see why in a moment. x1, x2, square root 2 of x, 1, x3, square root of 2, x1, xn, and we'll also do square root of 2, x2, xn, x3, up to eventually square root of 2, xn minus 1, xn. want to add one more element to the vector x, which will always be the same, it will be 1. So what is the dimensionality of this embedding? What is M? Maybe we'll write it here. M, what is it? Okay, let's just count it. There are n of these, right? And then there are also n of these, right? How many of these?
N squared.
Not n squared, because we're not counting any one of the combinations. We're counting each combination just once, and also we don't have here the terms where both elements are the same, indices are the same. So what is this?
And then the minus 1
Over 2, right? And then there's this additional one. So it ends up being n squared over 2 plus 3n over 2, because we have 2n minus n over 2 plus 1. So this is m in this example. Now, the fact that I put here these prefactors, you will see in a moment why I did it, because when we will write k, it will be helpful. But of course, I want to point out it doesn't matter at all for what can be done with this embedding, because of course, this can be absorbed into the weights. You know, the prefactors that you put in front of each one of these elements can be absorbed into the linear weights that will be implemented later. So it's just for my convenience. And it's just, as you will see, it will allow me to write the kernel, this function, in a very compact and neat way. So let's do that. So let's imagine that we have two vectors. And now I will use, let's call them x. I'll put the indices at the top because they're also the elements of the vector. So I have vector 1, which is x11 up to x1n. And I have another vector x2, which is x21 up to x2n. And I want to write down what is the kernel associated with x1 and x2, which is the dot product of phi of x1 transpose phi of x2. So what is it? So we will have here let's start with this element, okay? So this element will be just 1 times 1. So this will be 1. And now let's do these elements. So it will be x11 times x21 plus x1. So what will we get from all these elements? Okay, maybe I'll write it explicitly. Sum over I going from 1 to n times 2 because there's a square root of 2 twice, and x1i times x2i, right? So this is just the dot product in the n-dimensional space. This is just x1 transpose times x2, right? Now let's go to these elements. So in these elements, we will have sum over I, x1i squared times xi2 squared, right? And then I will have, from these elements, I will have a 2, and I will have a sum over, say, I larger than j, or I smaller than j. xi1, xj1, x21, xi2, xj2, right? That's all, that's everything that we have. Okay, so what do we have here? This is 1 plus 2 x1 transpose x2. Now, what is this? What is this? Yeah. So, exactly. So this is x1 transpose times x2 squared. Why? This is the sum over I, x1i, x2i. And now if we square this, we will get terms where it's the same I in both, okay, so we'll have here, this is sum over I, x1i, x2i squared. So there will be two types of terms. There will be terms where when I squared it, I had the same index in both, take the same index in both parentheses, and this will give me exactly this. And there will be the terms where I take a different index here and here, and you can check that you'll get exactly this. Okay. But now this is very nice, because what we have here then is 1 plus x1 transpose x2 squared. So you see now that the kernel, again, so I'll just write it now in just the result. The kernel of two vectors, n-dimensional vectors, is this thing. And so actually to calculate it, even though we can interpret what we're doing as a dot product in this n square over 2 plus 3 n over 2 plus 1 in this m-dimensional space, to calculate it, I only calculate a dot product in the n-dimensional space, right? And the effort is just as much, is basically the same as doing the regular dot product. I just add to it 1 n squared, okay? Okay, so so there's now another way to think about what we've done here is that you see that what we have here are using these functions, we can write down any second order polynomial in the elements of x, right? Linear combinations of these functions, right? Now remember that the decision plane, in the n-dimensional space is just a linear combination. In the n-dimensional space, therefore, the separating plane between category 1 and category -1 is going to be can be now any second order polynomial in the elements of x. So actually what we've done here is that instead of solving the problem, if we use the kernel method with this kernel, instead of looking for linear classifiers, in which the separating plane is a linear function of the x, we can implement any classifier where the separating surface, now it's not a plane, the separating surface is any quadratic function of the elements of x. Any one, because these functions span any quadratic combination of the elements of x. And we can generalize this further, so, and this is sometimes done. So another example is to generalize to d-dimensional polynomials. And now instead of starting like this and reaching this, I will start from this point, okay, so go backwards. So our kernel will be k of x1, x2 is equal to 1 plus x1 transpose x2 to the power d. And so the functions phi, sometimes they are called the features. The features, the functions phi, in this case, can be thought of as any d-dimensional combination, any combination of up to d elements from the X. I will not, show this explicitly. Any product of up to d elements of X, which means that if we work with this kernel, we're actually looking for a separating surface which can be any d-dimensional polynomial. What is the dimensionality M in this case, therefore? Okay, I will write down the answer. I will write down the answer and we will leave this for you as an exercise. It's M plus D over D. You can check that this matches for D equals 2. So you will get the expression that you're using here. And now,
why would you want to do that? Why isn't it enough to stay with the...
well, of course, so if we have if our separating surface can be any d-dimensional polynomial, then there's a richer range of set of dichotomies that we can implement.
Isn't there a limit to the dichotomy?
No, it's always limited by the class of dichotomies that we're considering. Now, yes, that's right. So the question is now, and I'm not going to go into that question at any depth in the course. But if you, in practice, you want to decide what to use, and if you have too many options, then you will not be able to learn and to generalize, right? But you are limited. But on the other hand, you want to choose a class of functions that can capture well the data. So it depends a lot on the type of problem that you're trying to solve, what you can assume about it. So it's in some extent, it's in practice, when implementing this in practice, it's an art and not only clearly defined. It's difficult to provide very clear guidelines, but some classes of problems. If the problem is, if you have good reason to think that the problem is linearly separable, then just use the support vector machine as it is. Anyway.
No, can you explain the motivation of choosing the kernel and then finding the features?
Well, so first of all, once we realize that we can use the kernel method, that we can just write down this kernel and use it, and that's all we need. If we can express it in some way, that's all we need in the learning algorithm and in the implementation of the support vector machine. then it kind of sounds like a good idea maybe to just start in this way and write the kernel. Okay? But for this particular case, there's a clear interpretation. I did not go through this, but if you would go backwards now from what I wrote here, then you can convince yourself that what we're really implementing is a product over phi of x's, where the elements of phi are all, as I said, all the combinations of up to d elements from the vector x, which means that the separating surface can be now any d-dimensional polynomial. Okay? So here we're implementing our separating surface is any quadratic, up to quadratic polynomial in the x's, and now we're generalizing this to a richer set of separating surfaces, which can be any d-dimensional polynomial. Maybe that's good, right? I mean, you know, with a plane is a plane, a d-dimensional polynomial is some kind of parabola or something like that, and a higher dimensional can be separating plane, can have a more complex structure. And so it can allow us to correctly to implement a richer classification. Another way to think about it, as I said, is that we're embedding in a higher dimensional space. But I think for your question, the motivation to use, say, d equals 3 rather than d equals 2 is if we think that a two-dimensional polynomial cannot correctly, the separating surface cannot be approximated well by a two-dimensional surface, a two-dimensional polynomial. Okay? Did I answer your question?
It seemed to me again like you were thinking first of m and then calculating c.
Right. So again, once the game that I played here is I wrote the kernel and then we need to interpret this. We need to interpret this as a product, as a dot product in some higher dimensional space, which can be done. And then if you do this, you see that the dimensionality is this. Now, but this really raises the question whether I could just make up any kernel that I want. Okay, so here I just, here I explicitly derived this in this way, and then I said maybe I can replace 2 by d. Can I write up any kernel that I want, and can any kernel that I would write be interpreted actually, okay, so let me write the question. Can any kernel k of x1, x2 be interpreted as a sum over I going from 1 to m? Did I use I for the answer? Phi I transpose of the x1, phi I of x2, with some appropriately chosen alphas, phi. That's an interesting question because if we would now just make up some k and plug it in, then we're actually not understanding what we're doing. But if we know that the kernel can be interpreted in this way, if this kernel is equal to something like this, then we understand that what we're actually doing is a linear classification in this higher dimensional space, right? So that's what I want to discuss now. And there's an answer to this question, which is given by a theorem called Mercer's theorem.
Why do you say linear classification?
Again,
Why that it's not
if I can write down the kernel like this and I do what I discussed, then what I'm actually doing, I can interpret what I'm doing as linear classification in the m-dimensional space. in this higher dimensional space. I can interpret what I'm doing as taking my n-dimensional vectors, embedding them into n-dimensional space by these functions, and then doing the regular supposed vector machine on the m-dimensional space. That's what the way we started with, right? If the kernel cannot be written in this way, then I have no idea what I'm doing anymore. So, Mercer's theorem tells us the following. So, assumptions. X, we're going to assume that X is confined, the examples are all confined to an n-dimensional box.
What do you mean box?
Box, I mean that each element of X is between some lower bound and some upper bound. So everything I will tell you is under that assumption. So the elements of X cannot be chosen in an unbounded way. And then assumption, actually, that's my assumption, not assumption. And so the theorem says that the series of functions phi I of X exists such that k of x1, x2 is equal to sum over I phi I of x transpose phi I, sorry, no transpose, because I'm writing explicitly the sum, phi I of x1, phi I of x2. If and only if, maybe I'll continue here. If and only if. So there are some requirements that the kernel needs to obey. One of them is quite obvious. It has to be symmetric with replacement of x1 and x2. So k of x1 and x2 must be equal to k of x2 and x1. Obviously that's the case. I mean, explicitly, if k can be written in this way, then it has to be symmetric with respect to replacement of x1 and x2. So this is necessary. This is necessary. And the other thing is that is the following. I will write and then I will explain.
G? What?
Yes, this is G. Oh, it's not clear. G. This is a G. Is non-negative and finite for any choice of the function G. So technically what is written here is for any function of x that I choose over the box, if I do this, if I calculate this integral, what I will get will be non-negative and finite. Now, I just want to provide some intuition for what this integral means. So imagine that instead of the x's, the position within the box, being continuous variables, we would have some very dense discrete points within the box. Okay. Okay. So imagine that our box would be just a set of discrete points. Then we're, by a function of the points, it's like assigning some value. I can think about the G now as a list of the values of G in each one of these points. So this is like a vector. And then what is this like? It's like an inner product of a matrix with the vector from one side and the other side. Do you see that? It's similar. It's not the same because it's in continuous variables. It's like the index, instead of the index of the variable, we have x1 and we have x2, and the vector is the value of G for each value of x1. This is like the list of the values of G for each value of x is like a vector. And we're doing the inner product, like it's the sandwich of some operator which takes two indexes, like a matrix. It takes one index, which is x1, and the other index is x2. And we're multiplying by the vector, the value of the vector at x1 and the value of the vector of x2. So this is like a generalization of something like a matrix Kij, Gi, Gj, where the indices are now replaced by the continuous variables x1 and x2. So this is like something similar to this, and therefore, if this was a matrix, what we would say is that this requirement is that this matrix is positive definite, semi-positive definite, non-zero, that this thing is non-zero for any choice of a vector. When we're writing this, something like where the index is a continuous variable, we call K not a matrix but an operator. So we say that this is K is a semi-positive definite operator. Okay. So you can think for yourself why it's true that if K can be written in this way, then this condition will be met. Okay. It's quite easy to check that. But Mercer's theorem tells us also the opposite, that if you make up some kernel and it obeys these two conditions, then it can be interpreted in this way, okay? Except for one thing that I didn't write explicitly so far. Can I still write something here?
No.
No? Okay. So I will write it with red here, but note the list of 5 might be infinite. So typically, it's not that you can write the kernel for most choices of the kernel that you will make up. Okay, so for this example, we wrote the kernel like this, and it actually can be written as a finite sum over some 5. But in general, typically, if these conditions are met, then you can write the kernel in this way, but this sum is an infinite sum. Okay, so this is typically infinite sum. And you might wonder what do we need to do in order to find if we really care about it. If suppose we write some K and you check that it obeys this condition, is there a way to find what are the 5 that correspond to this sum? So actually there is an answer to that. Maybe you know what, I'll give you, so how many people here studied physics? 1, 2, That's all? 3, 2? Okay. 3, kind of. Quantum mechanics. Studied quantum mechanics? Okay, so I will give you this as a riddle to try to think about it. What are these 5? I don't know if you will come up with the answer, but I'll give you the answer after the break. So let's reconvene at 5 minutes after 1. זה לא מפלט, אני מתעסק, זה כמו כל דבר. KIJ, GIJ. אוקיי, כי אני אומר, מה יש פה? אני כאילו עובר על כל, אם אני חושב על ה-X1 ו-X2 בתור כאילו אינדקסים, הם עכשיו רציפים, כן? ה-K הוא פונקציה של X1 ו-X2, ואני חושב עליהם כאילו כאינדקסים של איזה מטריצה KIJ. אבל אני חושב על זה, ההקבלה של שני המספרים האלה זה כמו האינדקסים I ו-J של מטריצה. אז מה אני עושה פה? אני עובר על כל הערכים של X1 ו-X2, ואני מסכם בהכפלה של K G בנקודה X1, G בנקודה X2. אז אני כל מה שניסיתי להגיד שזה דומה למצב שבו יש לי מטריצה שיש לה שני אינדקסים. אני מסכם את כל האיברים של המטריצה מוכפלים בערך של וקטור בנקודה המטריצה ב-IJ. IJ זה כמו X1 X2, מוכפל בוקטור בנקודה I ווקטור בנקודה J. לא ברור? מה? לא, זה בהגדרה, אם מטריצה מקיימת שהדבר הזה הוא לכל בחירה של וקטור G גדול שווה 0, אנחנו אומרים שהמטריצה הזאת היא סמי פוזיטיב דבק. כרגע אני מסתכל על הביטוי הזה ואני חושב על K כפונקציה של X1 ו-X2. בסדר? אני רשאי לחשוב עליו ככה?
אני לא ככה. K הוא הכפלה של
אבל K זה איזושהי פונקציה, בסופו של דבר K זה איזושהי פונקציה של X1 ו-X2. ואנחנו עכשיו שואלים, כל הדיון פה, אנחנו לא יודעים האם בכלל, את המצאת איזשהו K, נגיד שכתבתי את ה-K הזה. אני לא יודע אם אני יכול גם לתת לאינטרפרטציה כסכום כזה על הפעם, אבל זה איזושהי פונקציה של X1 ו-X2.
מה זה I ו-J?
אני מנסה לעשות הקבלה, אני מנסה לעשות אנלוגיה, זה לא, אין I ו-J, פה יש X1 ו-X2. I מקביל ל-X1, הקבלה היא ש-I, אוקיי, האנלוגיה, כל זה יותר במפורש. האינדקס I נחשוב עליו בתור X1, האינדקס J נחשוב עליו בתור X2, G של X1 נחשוב עליו כאילו באנלוגיה לאלמנט ה-I של הוקטור G, G של X2 נחשוב עליו באנלוגיה לאלמנט ה-J של X1 ו-I באנלוגיה ל-I שתתפס טוב בסדר. כן, זה כמו שבאמת G של X1 זה G של X2 ו-X2 ו-K של X1 X2 נקרא לזה KIJ. במקום תלות בשני משתנים רציפים הייתה תלות באינדקסים עתידים, אז בעצם אם היית כותבת את האינטגרל, אם היית קרבת את האינטגרל הזה כסכום על הערכים של הפונקציה בכל הנקודות, כן, הרי אינטגרל אפשר לחשוב עליו. אז תשכחי את זה שזה דו-ממדי, תחשבי בואי נגיד שזה אין ממדי, זה שני אין ממדי, נכון?
אם I ו-2 אז KIJ
אז שנייה, את צודקת. X1 הוא בעצמו וקטור אין ממדי, X2 הוא וקטור אין ממדי, אז K הוא פונקציה של שני אין מספרים. והאלמנט, כל האלמנטים של הוקטור הזה וכל האלמנטים של הוקטור הזה. נכון, אז אני... עוד רגע. אז עכשיו, בואי למשל נדמיין ש-N הוא 2. n הוא 2. או, אתה יודע מה? בואי נתחיל במקרה לצורך פשוט ש-n הוא 1. אם n היה 1, אז הייתי יכול לחשוב על זה באמת שה-x שלי שנע בין איזשהו שני ערכים. במקום ערך רציף של x אני חושב עליו כאוסף של ערכים פרידים, וזה כמו וקטור. אז זה היה לך יותר קל לחשוב על זה, כי אז אם ה-n היה ממד אחד, וה-x היה פשוט מספר, היו פה שני מספרים, ואז, לא, אז x אחת הוא מספר, ואני חושב על הערכים של g בכל אחד מהמיקומים האלה כווקטור. אוקיי? עכשיו נכון שבפועל אנחנו בדרך כלל עושים את זה לווקטורים יותר רבים, נניח שאנחנו ממדיות 2. x1 הוא ערך בתוך הריבוע הזה. אז אני עדיין אחשוב על הערכים של g בכל, אני אחשוב על אנלוגיה למצב שבו x הוא לא רציף, אלא יש הרבה ערכים צפופים. כן, זה x1. ו-g של x1 זה הערך של g בכל אחד מהמקומות האלה. אז זה נכון שכאן אנחנו מציירים את זה על ריבוע, משהו משטח נומרי, אבל הייתי יכול לקחת את כל המספרים האלה ולייצר מהם וקטור אחד ארוך. x1 הוא צמיחת המשתנה רציף שיכול להיות בכל מקום על הריבוע. נכון? לא? x1 הוא משתנה שיכול להיות בכל מקום על הריבוע. זה וקטור דו-ממדי? נניח ש-n שווה 2. x1 הוא וקטור דו-ממדי, x1. זה הערכים. אוי, לא, 1 ו-2 בראש עכשיו, זה לא הדוגמאות. זה לא כאילו המספרים של הדוגמאות, המספרים של הדוגמאות יש פי דוגמאות. זה פשוט שני ערכים, זה כן דוגמאות, אבל זה לא האינדקס 1 ו-2 הוא לא מספר הדוגמאות. האינדקס 1 ו-2 זה סתם איזה שהם שני וקטורים. הם יכולים להיות חלק מהדוגמאות, והם יכולים להיות גם כשמיישמים, כשמריצים את ה-XVM לאיזושהי דוגמה חדש. כן, זה איזושהי דוגמה. אבל הם עצמם וקטורים דו-ממדיים. או אין-ממדיים. נכון, אבל הוא יכול להיות, אני רוצה עכשיו להבין מה אני יכול לומר על הדבר הזה כפונקציה של שני הוקטורים האלה. לא חשוב, יש לי איזושהי פונקציה של שני משתנים, אני רוצה להבין תכונות שלה. לא מבין למה, אני לא אמרתי שזה משתנים, אני אמרתי אבל אני לא יכול לעשות.
סימן זה מלא נקודות על ההחלטה הזאת?
לא, אני לא חושב שאמרתי שזה משתנים. אני אמרתי אני מנסה פה לעשות, אוקיי, בואי נתחיל מזה שהקרנל הוא פונקציה של שני אקסים, כל אחד מהם הוא משתנה שנמצא בתוך הטווח של הריבוע. אם אמרתי משתנה מקרים בקונצפט, לא התכוונתי לזה. בסדר? זה שני וקטורים, איפה הם חיים? הוקטורים האלה זה וקטורים שאמרנו שהערכים שלהם מוגבלים לקופסה, אז ה-x1 נכון, x הוא נקודה בתוך הקופסה. עכשיו אני מייצג את כל, נכון, ואני מייצג עכשיו את כל הערכים האפשריים של x. כל הערכים האפשריים של x הם בריבוע.
מה זה אפשריים? אתה נותן x1 לשטוף חלק
תראי, אני כתבתי פה פונקציה של שני וקטורים. שני וקטורים יכולים לכל דבר. נכון ש... אני עכשיו דן באופן אבסטרקטי בתכונות של הפונקציה A. אני רוצה להבין מה התכונות של הפונקציה. אני רשאי לחשוב עליה עכשיו כפונקציה של שני אינפוטים. לא דוגמאות. נכון? רשאי? אז יש פה שני משתנים, כל אחד מהם הוא וקטור דו-ממדי. עכשיו, אני מנסה פה לעשות איזושהי אנלוגיה, שאני לא... אני מבין שזה קצת קשה, אני לא חושב על הדברים כאלה בעבר, אבל מה אני יכול לומר על הביטוי הזה? כאילו, אני חושב על x1 ו-x2 כאילו, כאילו, נגיד g של x1. g של x1 זה פונקציה שמוגדרת על הריבוע. נראה שאנחנו נצטרך יותר זמן כדי שאני אסביר לך את זה. לא, כי אני כמעט סיימתי. פשוט אני עצמי צריך עכשיו הפסקה, פשוט אני מציע שנדבר, כאילו, תבואי לדבר איתי או באמת אגב. חשוב כמובן שתבין את זה. אני חושב שזה לא יתקע לך יותר מדי עכשיו המשכתי, אני לא אמשיך את זה הרבה זמן. אני חושב שהיום אחרי השיעור אני לא יכול, אבל אנחנו כן יכולים לתאם בו. בסדר? כן, בדיוק. הציים האלה זה בדיוק. מה זאת אומרת סט אורתונורמלי?
סט של פונקציות אורתונומליות אנחנו מכירה
אבל שאלה מה הקשר בין הפונקציות האלה ל-K? סט אורתונומלי של מה? לא כל סט אורתונומלי שיכול לקבל ואתה יכול לפרש את ה-K
שינרמל את כל אלה.
יש קשר יותר מפורט ל-K. על מנת שאפשר יהיה לכתוב את זה. בעצם, דרך אחת לחשוב על זה, ונניח שאתה יודע כבר ש-K שאתה יכול לכתוב את זה. מה זה אומר על הפונקציית פאי?
זה לחסם את המטריצה של המכפלה הפנימית, המטריצת הגרם. כאילו לא למדתי פיזיקה, אבל אפשר גם באלגברה ליניארית.
נכון, גם באלגברה ליניארית, אתה צודק ב100%. גם עם האנלוגיה הזאת אפשר להבין את התשובה.
נכון, איך להציג את המטריצה הפנימית?
זה כאילו פונקציות עצמיות. אז אם זה אלגברה ליניארית, ברגע שאנחנו כותבים את K ככה, ואם כמו שאתה אמרת, גם הפאי הם פונקציות אורתונורמליות, אז קל לראות שאם ככה לא רק שכל אחת הפונקציות האלה חייבת להיות, אם זה היה זה וקטורים, בגלל שהיה צריך להיות וקטור עצמי של המטריצה. עכשיו אנחנו כבר אמרנו שהמטריצה הזאת היא מטריצה סימטרית וסימטרית, אז יש לה באמת, הוקטורים העצמיים שלהם אורתונורמליים, אפשר לבחור אותם כך שהם אורתונורמליים. ולכן, ה-G'ים האלה, באנלוגיה, אז ה-G'ים האלה זה וקטורים עצמיים של המטריצה, ובאנלוגיה, ובמה שבאמת אנחנו יודעים בו, שזה אופרטור רציף, אז זה פונקציות עצמיות שמקיימות שאינטגרל של K אצל הפונקציה, ייתן משהו פרופורציוני לפונקציה. אני רק שנייה צריך עכשיו אני מסתכל על הרשימות שלי.
לא, זה בקשר ל-G, כביכול G אנחנו... יש כפר כלשהו ל-G, בדרך כלל זה מה שיש לנו מרחב לגדול. ואחרת אני יכול כביכול G משוגעת קיצוני של E ב-E 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 ב-E
כן, אני מאמין שיש, אני קצת מתרשם בדיוק המתמטי. אני לא בטוח מה בדיוק, אני לא זוכר מה בדיוק צריך לדרוש על ה-G. אני מניח שיש איזשהו סייגים כאילו...
היה לנו שכאילו במקרה הסופי, כאילו אפשר כזה לחלק לחלקים, כאילו חלקים, את האפס, את האחד, את השתיים, את האל, ואפשר להסתכל על ואפשר להסתכל על השפה, ואז כאילו פשוט מקבלים קטע. שזה פשוט מבין, ואז היה לנו את החיבוריות שבמקרה הסופי זה היה ריטה, כאילו בין האלורן שמתחיל ל-I ו-J. ה-J, היה J-I-J. אז היה J-I-J שבמקרה הסופי זה באמת הקביל ללת, ובמקרה כאילו הרציף
כאילו באופן דומה לקחת את כאילו להציג מטריץ שפונקציה זה כאילו, זה כמו איזשהו וקטור אינסופי והמטריצות האלה זה כמו פונקציות בשני משתנים. אם כאילו, אם זה היה כל אחד מספר הכי בסיסי, אני לא יודע, אם הם מבזבז, אז לא חייב לחשוב על זה ככה. זה דרך כזה...
זה לא, זה כתבים של הבן אדם עם התמונה. מי? שלום חביב.
זה לא מטריצות, זה...
הוא היה לוחם אצל
לא, בסדר. את מסתכלת על הכתבה, כאילו, על אבליואציה של הקייס בנקודה מסוימת.
קראתי לגבי התרגילים, תקציב משהו אחר.
כן, להעביר את הזמן
מקבלת
שם.
שני
אני
זה עכשיו שאנחנו רוצים לחשוב כאילו
סבירת הקרדומית.
באיזה תנאים היא בכלל יכולה אפשר לכתוב אותה ככה. כאילו
אפשר תרגילים? הגשת?
זה לא
קטנות, אני לא יכולה
לא שופט.
צוחק אפילו מאוד.
האמת לא, שופט בלב.
התחלתי רק לכתוב דיסקשן לפי
גם כאן. לא סיימתי את קונטרול בזה. אז עליתי בסיכותים של הכל. לא, ברור, אני לא... כאילו, אני לא אוכל את זה, אבל זה לא יהיה איתך כמו שאלה, זה יודע כזה.
כן, אני אראה כל היום.
באמת? לא, זה ייקח שעה.
ל-X אחד יש X אחד בווקטור ממדי.
אין לזה הסבר מה. אבל באמת, מתי זה צריך?
מה? אני חושב שמאז בסיסקו כאלה של חסרים כאלה, אינדקסים בטוח.
טוב, אני לא יודע, לא הסתכלתי, לא הקשבתי לך.
כן, אתה רואה שזה לא חשוב, אבל
זה לא כזה.
Okay, I want to comment because of some questions that I got in the break. By the way, I forgot to use the microphone. So the second time, did any one of you try to look at the recording from Thursday? And was there audio? So, yeah. Because on Thursday I also forgot to use the microphone. So one thing that I'd like to ask is to try to remind me, because I tend to forget. I don't know if you know, if I don't use the microphone, if the recording still has some audio or not.
It has audio, but
It's not less good.
Yeah.
Okay. Now, following questions that I got, I want to point out that just what I'm doing right now, this discussion of Mercer's theorem, is kind of mathematically difficult for those of you who didn't look at things like this, and I know that for some of you it's not so easy to understand it. I think it's a good idea that you will take the effort and think about it and come to talk with me or with Neta or among yourselves and try to understand what I was saying here. But I know that for some of you it was not clear that listening to what I was saying right now. Okay, but we're not going to dwell on this for a long time. Okay, I just want to say a few more words about this and then we will move on. So I was asking the question, suppose that I write this kernel suppose that I give you the kernel, is there a way to find what are these five? Because the theorem, Mercer's theorem tells us if the kernel obeys these two conditions, then I can write it in this way. And some of you kind of found the answer. one way to do it is to think about the analogy to matrices. So if I would think about K not as a function of two continuous indices, but as some matrix with some discrete indices, then it's a bit easier to think about it. Then you know, for example, that a matrix that is symmetric can be diagonalized, you know this, right? With a set of orthonormal vectors. What I'm saying now here is really not critical for anything in the course. It's just for, you know, for the because it's interesting. Might be interesting to some of you. So in that case, and then if you think about it in that way, if you take what I wrote here and think about the analogy to matrices, maybe it will, if we want to think about it more deeply, it will be easier for you to understand that in fact in that case these functions phi are nothing but the eigenvectors of this linear operator. Now what do I mean by this in the continuous case? And this is why I asked who here studied quantum mechanics, because in physics we do this a lot. So I'll just write this. If you don't understand it, don't worry. And if you do, it might be interesting for you that the phi i's are eigenvectors, eigenfunctions of the operator K. And what this means is that if I take the function phi I and look at the integral of K of x1, x2, phi I of x2, dx2, so this is like the product of a matrix with a vector. So in analogy with matrices, if I would say that a vector is an eigenvector of a matrix, this would mean that I would take K multiplied by the vector and get something proportional to the vector. So here I take K of x1, x2 multiplied by phi of x2, integrate over x2, and I remain with the function of x1. And the statement that phi I is an eigenfunction of K is a statement that I get something proportional to phi I of x1 with some prefactor, which is I will call the eigenvalue. And these eigenvalues are positive or non-negative because K is a positive definite operator. And when I write something like this, there's still a question of normalization. If I multiply phi I by a factor, I will still get an eigenvector or eigenfunction is defined up to a prefactor, and so there's a specific choice of the prefactor that you need to put in here in order for all this to work. I will not write it explicitly. You can think about it if you want. So the fact that K is symmetric implies that just as much as a symmetric matrix can be diagonalized with a set of orthogonal vectors, with a basis of orthogonal vectors, a linear operator defined on a box, on an n-dimensional box, that obeys these conditions, that obeys this condition. It's confined to an n-dimensional box, and it obeys these conditions. Can be, in a sense, diagonalized by a set of functions which can be in infinite series, but they also can be chosen to be orthogonal to each other, and the eigenvalues are positive or non-negative because of this condition, and that's important for this part. And once you realize that you can do this, you can see how to write K in this way. Anyway, from our point of view, let's backtrack a bit. The reason we went into all this is that we saw that in initially when we defined the kernel method, we started by defining these phi's, right? We defined these phi's, and then we saw that we can write everything that we do when we implement the support vector machine in terms of this kernel. And then we asked ourselves, can we make up any kernel that we want? And can it then be interpreted as a sum over, as a dot product in a higher dimensional space? And now Mercer's theorem tells us that the answer is yes, provided that these conditions are met. And so what I want to do last is just mention some other kernels that people sometimes use. And then we will move on to another topic. Before I write examples of other kernels, I want to point out one other thing. I drew in the beginning of the previous lecture, I drew kind of a graphical representation of the architecture in which we have an n-dimensional vector. We generate from each n-dimensional, we generate from it m numbers, which are the phi's, and then we do some linear classification on these phi's. But when we think about the dual problem, suppose that we work with this kernel method, we provide a set of examples, p examples, and we set the alphas based on these examples. Then when we want to implement this particular support vector machine that we trained, we can think about what we're doing or represent what we're doing graphically in a somewhat different way, which is that I have the input vector x1 going up to xn. And remember that y is equal to a sum over, it's the sine of the sum over mu, alpha mu, y mu, k of x mu x, right? So after we ran the Adatron algorithm, we found the alphas. We have p numbers, p alphas, and if I give you a new x and you want to categorize, this is what you need to calculate. And so this I can represent graphically by going not from n numbers to m numbers, but from going from n numbers to p numbers, right? I need to, whenever I want to calculate the categorization for a new example now, so that I haven't seen before, I need to calculate k of x1, k of x1 x up to k of xp x. And so each one of these numbers is some nonlinear function of all the entries of x. And then I do some prescribed linear classification, with alpha 1, alpha 2, up to alpha p, with these numbers. And moreover, typically it's even much smaller. The dimensionality of what we need to implement is much smaller than p because the alphas are very sparse. Typically, only a small set of examples are the support examples, and for the rest the alphas are 0. So you will see in a moment why I'm pointing this out. And now I want to write down some examples of kernels that people often use, or sometimes use. One is called the Gaussian kernel. So one of them, okay. One is actually the polynomial kernel that we discussed. So for the polynomial kernel k of x and x prime is equal to 1 plus x transpose x prime to the power d, and d can be chosen as you wish. And so this is an example where this actually implements an embedding into a finite dimensional space, as we discussed earlier. But another example which is commonly used is the Gaussian kernel, where k of x and x prime is the exponent of minus x prime squared divided by 2 sigma squared. And for this kernel, this kernel obeys the requirements of Mercer's theorem over a finite space, but not the embedding is into an infinite dimensional space. Okay, the set of 5 is infinite. It's an infinite series, and this is also sometimes called the radial basis functions. See what I want to say. Radial basis function kernel. Sometimes this term is used to represent any kernel that depends only on the distance between these 2 points. Okay, and then I want to mention another kernel which is conceptually interesting, and this is the logistic kernel. So for the logistic kernel, k of x and x prime will be defined as the hyperbolic tangent of say beta x transpose dot x. Actually, we can even let's write this x transpose dot x prime plus some number b. Okay, and this is a positive definite, meaning that it obeys the requirements of Mercer's theorem for some choices of beta and b. But the reason I'm writing this kernel, one of the reasons I'm writing this kernel, is that if you would imagine that now you implement the decision of the support vector machine with this kernel after you trained, so you have all the examples x1 up to xp, then what you're actually implementing corresponds quite directly to a conventional model of a neural network. In general, these functions, if you work with a Gaussian kernel and a polynomial kernel, these functions are some complicated nonlinear functions of the inputs that we don't really imagine that corresponds even conceptually to what a neuron might do. But with this kernel, what we're calculating is actually some linear combination of the weights of the inputs, right? So the weights of the weights appearing here are the elements of the example, say here, of x1, right? So it's a linear sum over the inputs x with some weights. This is multiplied by some number. We add another number, and then we pass all this through some nonlinearity, some saturating nonlinearity. So this conceptually, if you look at this plot and think about what what you actually do when you work with a logistic kernel, you implement something which matches what what we would call a two-layer feed-forward network does. Receive the inputs, we pass through another layer of neurons whose responses are given by this hyperbolic tangent, and then we do another linear classification on the output of these neurons. So again, conceptually, this means that at least for some choices of beta and B, if we're working with a logistic kernel, at least what we can learn with the support vector machine with this kernel corresponds to what we can do with a two-layer neural network with these types of neurons. Okay. So x1 up to xp are the examples that we trained on. So x is a new example. So the idea, we trained on p examples, okay, and now we have our support vector machine that we use to try to generalize to new. I provide you a new x, and you need to decide whether you categorize it as 1 or minus 1 based on what you've learned from the p examples. The p examples are now fixed. You don't learn anymore. You now just try to categorize some new examples. So that's the x. The new. I give you a new x. I no longer tell you what is the answer. If it should be so. For the p examples, I told you for each one of them if it's categorized as 1 or as minus 1. You've learned the alphas based on using support vector. Now I give you a new x, and I ask you based on these examples, do you predict that it's 1 or minus 1?
While training, what do you do the kernel?
What?
While training, what do you?
While you're training? No, there's no x. While you're training, you're working with the x1 up to xp. You train based on x1 up to xp, which would come with a label. Each one of them comes with a y1 up to yp.
But the k is on two vectors?
So I think this is something that is confusing you, and we will need to discuss and make sure that you or anyone else who doesn't understand it understand. The k is given. The k is some function. The k is say this function or this function or this function. It's fixed. And all we're doing is something with the examples, x1 up to xp. And for those of you who don't understand this yet, and it's confusing for you, it's important that you understand this, but we'll need to do it later, okay? You're very welcome to come and discuss this with me and with Neta. Okay. I think this is what I wanted to tell you about support vector machines. And I want to discuss now some other forms of learning. So the topic now will be gradient-based learning. So in the examples that we've done so far, the binary perceptron, linear perceptron, binary perceptron with the additions of the support vector machines. We had some goal, which was to categorize the examples correctly and maybe optimize some measure of error. In the linear perceptron, we did that. In the current support vector machine, we wanted to maximize the distance of the closest point from the separating plane. But once we set up our goal, we translated this into an optimization problem. We had some function of the weights that we wanted to optimize, and we understood what needs to be done in order to optimize this. In the linear perceptron, we could write down an explicit expression for the weights, analytical expression. In the binary perceptron support vector machine, in order to implement this optimization in the support vector machine, say we had the Adatron algorithm. But sometimes we want to do something a little bit different. We have a more complicated architecture, complicated structure of our classifier. What the classifier does depend on some parameters, maybe some weights inside a neural network, and we want to optimize it. And I want to discuss a general methodology in order to do that. So we go back to the context of a continuous function. Approximation of a continuous function. So we're no longer now considering classification. We're going back to approximating some continuous function. So, if a continuous function matches an input x to some function of x, a scalar function. And what we are going to imagine, just to lay out the problem in a very general sense, in a very general way, is that we have some, say, neural network. I'm saying neural network because we're thinking about neural networks, but this is really can be very general at this point. Which maps x to some output y, and this output is a function, of course, of the input x, but it's also a function of some internal parameters within the network. I'm going to think about these parameters as some weights within the neural network. Okay? So the output of the neural network depends on the input, it depends on some weights. And we want to set the weight such that we will approximate this function as well as possible. Okay? And so our goal is to learn W based on examples x mu, y mu.
How is it different than the linear system?
It's exactly the same, except that it's not linear anymore. So, as long as the relationship between y and x was a linear combination of the x's, and then the weights were just the coefficients, then we knew how to solve this, to write an explicit expression for the best w's. Now, the relationship might be more complicated, and maybe we don't know how to do that. And so the approach that we're going to take is still that we want to minimize the training error, as before. Still the same. So I remind you that training error is, we wrote 1 over p, sum over y going from 1 to p, f of x mu w and a minus y mu square. So we're going to work with a quadratic measure of the error. And again, the difference now compared to the linear case is that this might be f might be complicated, and maybe we don't know how to write equations that w must obey. Okay, so the approach that we might want to take instead is called gradient descent. And in this approach, the idea is that we try to kind of numerically find a minimum of this function. So we start from some weights, and then we just go along the gradient of this function with respect to w. Okay? So this function is a high-dimensional. W is n-dimensional. It might have any dimensionality. It didn't specify here how many weights there are in the network. Maybe it might be n-dimensional, as in the linear perceptron. It might be even higher dimensional. We'll discuss this in a moment. There are a set of weights inside the network, and so this whole thing, the training error, is a function of the weights. It's a very high dimensional function, but we can check if I give you a certain set of weights, you can calculate the training error. That's fine. You know how to do it. You can also calculate what is the derivative of the training error with respect to each one of the weights. And then a general standard approach for minimization, numerical minimization of function, is that you just go in discrete steps, small steps along the gradient, which guarantees that you're going to make in each one of these steps, if they're small enough, you're going to decrease the training error, and hopefully you're going to end up at a minimum. Well, you are going to end up at a minimum. What might be the problem? Right, you're going to end up in a local minimum. It's often true that these functions, the training error for typical networks, typical problems, have multiple minima, and so that's the best you can hope to do. Well, you can also maybe try to start at different initial starting points for the weights, but let's just write down and hope that you will find eventually a global minimum, but usually what you get is some local minimum. And so the idea, I want to write down what explicitly you do in each step. So in each step, you change the weights delta W as some minus eta times the gradient with respect to W of the E training of W. Which can be written, each one of these steps can be written as a sum over all the examples. So this, in some sense, this is like an analogy of the cycling over all examples that we discussed previously in the Adatron algorithm and the perceptron algorithm, but we do it in one step. In each step, we do an update which is based on all the examples, because the training error depends on all the examples. And eta is called the learning rate. And you do this until the gradient with respect to W, you stop at some W star where the gradient of the training error, the gradient with respect to W of the training error at W equals W star is close enough to 0. Okay, then you say, okay, I found the minimum, and that's where you stop. What are the considerations in choosing the learning rate? Well, if the learning rate is too large, then you're not really going in a direction that necessarily decreases your function, because gradient is a measure of the change in the function for small changes, right? So you want to take small enough steps in order to really follow the direction in which the function decreases as fast as possible and go to a minimum. And if eta is very small, it will take longer. So there's some trade-off here. We'll discuss this trade-off a bit more later in a slightly different context. And the other thing that I want to mention is that this type of learning is called batch learning. Because you have a set of examples, and in each step of numerically what you do is a set of steps. Each one of them depends on all the examples. So this is just a general, very general approach to learning. And I want now to connect it to a particular type of architecture, which is now very widely used, and this is the deep feed-forward networks. Well, feed-forward networks are deep. They can be deep or they can be shallow, but feed-forward networks. So the architecture looks like this. I will now, instead of going from top to bottom, inputs in the top, output at the bottom, I will go from left to right. Our inputs are x1, x2 up to xn. And then the idea is that we go through a set of layers. So the first layer, each one of the neurons receives the inputs from all these neurons. And let's call the output of these neurons sigma I. And I'll put here an L. So I'll put here 1 because there will be additional layers. But let's start with this layer. So the 1 is the index of the layer, the I is the index of the neuron within that layer. And the output of the ith neuron within this layer depends on all the inputs from the previous layer. So this is sigma. What is it can be confused with?
I thought it may be delta.
Delta? Okay, so I will try to be more close to sigma. Okay. So you know what, before I write down what is the relationship between sigma I and the x's, I will actually draw another layer. The number of neurons in each layer doesn't need to be the same. Okay? And again, and each neuron in this layer, its output is a function of all, in principle, of all the neurons in the previous layer. Okay? So the architecture is kind of like this. And now I want to write what we assume for the relationship between input and output of each neuron. And so I will write that sigma IL is some function. So what the neuron does, it sums up all its inputs with some linear weights. So Wij sigma L minus 1 j, and j goes from 1 to the number of neurons in the previous layer. So let's call that n L minus 1. Okay? So the neuron sums up all its inputs with some linear weights. Maybe there's some additional number here, BIL, and all this summation goes through some nonlinear function. Remember, we discussed the fact that we often model activity in neural networks in this way. In the first presentation, in the first lecture, I discussed dynamics, a simple model of dynamics of neural networks. And actually what I'm writing now is a steady state of these dynamics. Okay? And the G, if you remember, is some nonlinearity. And the typical structure of this nonlinearity, G of X, is that first of all, G has to be positive because G kind of represents a firing rate. Although technically when this is used for machine learning, sometimes this G is between -1 and 1 instead of being between 0 and 1. But now let's imagine that it starts from 0, and it's also typically bounded. So when implementing this for machine learning, implementing these kind of algorithms, G is typically